Okay, so this is the video accompanying Lecture 1 from Math 31 AH. And right, so what I wanted to do was actually use this Feynman principle that I was telling you about on Friday, which more or less says that what you ought to do to be a smart person is to have a list of problems in mind that you'd like to solve. And every time you learn something new, you test out what you learned against those problems in mind and see if it can help in solving any of them. So the problems, of course, that we want to keep in mind here are the problems from assignment one, okay, which was posted on Friday. And presumably you've had some time to look it over already and at least think a little bit about those problems, even if there are things that mean almost nothing to you. You've at least managed to read it once and maybe have some idea of what the problems are asking. So in particular, if I recall correctly, what problem one asks is, and I won't, what does it mean to keep something in mind? I'm not going to copy down exactly what it says, but what's my recollection of what problem one says? It's something along the lines of prove that the zero vector in any vector space V V is unique. Okay, and so how does lecture one help with this? So in lecture one, what's the new thing we learned that we can test out against this problem? Well, we learned what a vector space is, and so again, there's kind of a long definition. A vector space is well, what is it? It's a set V together with an operation of vector addition, which is denoted by the plus sign, and an operation of scalar multiplication, which is actually denoted by nothing. So I'll just draw a line here. And then there are some complicated axioms which govern these operations, and actually I think there are eight of them. But it's certainly important to understand what those axioms say. But if you're just thinking about this as a human being, basically the axioms say that that vector addition and scalar multiplication obey the usual rules of algebra. Okay. And of course, if somebody asks you what the usual rules of algebra mean, well, then you have to come back to these eight axioms and start telling them about that. But let's just keep this in mind as our heuristic, as our guiding principle. And then we want to see if understanding what a vector space actually is now sheds any light on problem one. Hopefully it does, because this is something that's supposed to be a direct consequence of the axioms. And first of all, what is the characteristic property of the zero vector in a vector space V? Well, the main feature of the zero vector is that for any V in V, so for any vector V in your vector space capital V, we have V plus 0 is equal to V. In other words, adding the zero vector to any vector doesn't change anything. And of course, I should say that this is also, you can write a second equation here, which is that instead of writing V plus 0, I can write 0 plus V. And these two things are the same, right? This V plus 0 and 0 plus V are the same. Indeed, one of the usual rules of algebra, of course, is that addition is commutative. It doesn't matter what order you add things up in. Okay, and so basically what we want to show is that there's only one vector with these properties. And so the vector space axioms guarantee that there's at least one. And what the problem is asking you is to verify that there couldn't be more than one. So, let's suppose that um, 0, 1 and 0, 2 are two vectors in V that behave like 0. Okay, and what does that mean? That means that for both of them, I have V plus 0, 1 is equal to V for any V in V. And I also have V plus 0, 2 is equal to V for any V in V. All right, and what does this say about the relationship between, let's see here, nope, between these two zeros, these two possible zeros, 0, 1 and 0, 2. Okay, whoops, that's not what I wanted to do. Let me start a new page, which I have somehow forgotten how to do. I haven't used this in a long time. Nope. There we go. Okay. Right. Okay. And to prove that the zero vector is unique, what we really want to show is that these two potential zeros are actually the same thing. Okay, so that 0, 1 and 0, 2 are the same. They're not distinct. They're just the one unique zero vector in the vector space V. So how can we prove that using this property that both of them have, namely that they're inert with respect to vector addition? They don't change anything. Okay, so let me write down the sum of these two zero vectors. So 0, 1 plus 0, 2. Okay, on one hand, this is equal to what? This is equal to 0, 1, right? And why is that? That's because adding 0, 2 to any vector does nothing, and my any vector I'm taking to be 0, 1. And also, I have 0, 1 plus 0, 2 is equal to 0, 2. And why is that? That's because adding the vector 0, 1 to anything, and in this case, my anything is 0, 2. Actually, I guess I shouldn't have. Yeah, no, that's right. My anything is 0, 2, so it just stays the same. All right, has no effect. Now, if I look at these two equations, you'll notice that the left-hand side of both of them is the same. Right, on the left-hand side of the first equation, I have 0, 1 plus 0, 2. And on the left-hand side of the second equation, I have 0, 1 plus 0, 2. Okay, and if those two things are the same, then that means that I can also equate their right-hand sides. Right? In other words, 0, 1 is equal to 0, 2. And that's it, right? That's it, just from the fact that the definition of anything that qualifies as a zero vector is that it has no effect when added to any other vector. I get that it has to be unique. There can only be one vector with this property. And the vector space axioms, I believe it's listed as axiom number 3 in the Lecture 1 blog post, is that such a vector exists. And the fact that it's unique is a logical consequence of those axioms. Okay, so it's not a supposition or an assumption. It's a consequence of suppositions and assumptions that we agree to make. Okay, so that pretty much takes care of problem 1. And now I'm starting to think about problem 2. So let's see, let me start a new page. And what was problem 2 even about? So problem 2 was about, this is about linear independence. Okay. All right, so there's a good chance that when you first laid eyes on problem set 1 on Friday, you didn't know what linear dependence and independence meant, but now you do because you've read the lecture 1 post. All right, so let's see. What did problem 2 ask after all? So if I recall correctly, there are 3 parts, and so what was the first part? The first part was show that if a set, let's call it S, consisting of some vectors v1 through vk in a vector space V contains the 0 vector, then it's linearly dependent. All right. So what does that mean? That means that my set S, okay, I'm being told something about it. It actually looks like this. So I can assume, really without loss in generality, that let's say the vector named v1 in my set S is the 0 vector. So I have 0, v2 up to vk. That's what my set looks like. And I'm trying to prove that no matter what v2 through vk are, this set is linearly dependent. So what do I have to do? I have to show, need to show that there are numbers. Numbers are often called scalars in linear algebra. So numbers, what should I call them? T1, T2, up to TK, real numbers. Let me back that up. Not all equal to 0. This is the number 0, not the 0 vector, right? Such that what? T1 times V1 plus T2 times V2 plus all the way up to TK times VK is equal to the 0 vector. Okay, and that is the definition of what it means for a set S containing the vectors V1 through VK to be linearly dependent. Move this up a little bit and make some room. And what is my hypothesis? My hypothesis is that the vector v1 is actually equal to 0, right? That's what I'm being asked about in this problem. So this equation is the same thing as t1 times 0 plus t2 t2 v2, right, plus up to tk vk is equal to 0. And what I'm trying to do is I'm trying to find some numbers, t1, t2, up to tk, which make this equation true under the constraint that they're not all equal to 0. All right, so definitely if, no matter what v1, v2, up to vk are, if I just took, each of my t1, t2, up to tk to be the number 0, right, what would I get then? I would get 0 v1 plus 0 v2 plus all the way up to 0 vk, and that is definitely equal to the vector 0. And the reason for that is because 0 times any vector, no matter what it is, the number 0 times any vector, no matter what it is, gives you the 0 vector. Right? So that's actually something that is proved from the vector space axioms in lecture 1. Okay, so back to the problem at hand. How can I accomplish this without taking T1, T2, all of them to be equal to 0? Well, what I can do is, the thing is this. So I know something about 0, the vector 0. What I know about it is that if I multiply it, if I scale it by any real number at all, I'll get the zero vector back. So let me just, that gives me the freedom to make T1 any arbitrary non-zero number that I like. So let's make it the number 1. Okay, so I have 1 times the zero vector. Let me write 0v for the zero vector in v so that we're not confusing it with the number 0. Okay, and I'll write a little dot for scalar multiplication. All right, and then what to do about the remaining terms in this sum, t2 v2 up to tk vk. Well, why don't I just set t2 t3 all the way up to tk to be the number 0? Okay, and I want this to be presumably equal to the 0 vector. And is that true? Is it true that this is equal to the left-hand side is equal to the 0 vector? It is, right? It is true because 1 times the 0 vector is the 0 vector, and 0 times anything, the number 0 times anything, is the 0 vector. So this is just the sum of k copies of the 0 vector, right, which is definitely equal to the 0 vector. And so adding the 0 vector to itself k times, each pair of things, nothing changes, right? You add it to itself once, you get 0v. The next time you get 0v, all the way down to the end. And so I've shown that S is a linearly dependent set because I have found numbers t1, t2 up to tk, not all of them 0, which give me the 0 vector. All right, and so just to hammer it home, what were the numbers that I ended up choosing? So t1 is equal to 1, and then t2 all the way up to tk are all equal to the number 0, right? And definitely it's the case that not all of these numbers are 0, because t1 is 1. And when you take the linear combination of v1, v2 up to vk with weights t1, t2 up to tk, you get the 0 vector. All right, so we've shown that this set S is linearly dependent. And there's nothing special about v2 through vk or even k, right? So k could be any number. There could be as many additional vectors here after 0 as you want. And they have no special properties. They're just arbitrary vectors in a vector space. And as soon as 0 is included in this set S, you can employ this argument and demonstrate that S has to be linearly dependent. Okay, so that's that. And what was problem 2b? Let me think about that. It was something like, let me write down what it was in words. So it was something like the following. So show that if S is a linearly independent set, and let's say, and R is a subset of S. This might have been 2C. I don't know. Doesn't really matter. And R is a subset of S. Then R is also linearly independent. Okay, so let's see, how can I get started on this? Let me move this up a little bit, make it look better. All right, let's see. So let's write down what the vectors in S are. And I think at the very start of problem 2, it's declared that, so S is a finite subset of some vector space V. And I'm saying that it consists of vectors v1 through vk. So maybe to make this a little more concrete, so let's say suppose, for example, that k is equal to 3, all right? Why not? So that means that S is equal to a set of three vectors, v1, v2, v3. Okay, and I want to show that any subset R of S is linearly dependent, is linearly independent if S is. So let's say that R, what's a good subset of S to consider as an example? Let's take the first two vectors, v1 and v2. Okay, so what I know is that S is a linearly independent set. And what I want to show is that so is this subset R. And why would that be the case? So this is a good illustration of basic strategy in reasoning, in logic, which is often called proof by contradiction, which is that I assume the exact opposite of what I want to show, and then demonstrate by a sequence of logical inferences that that leads to a false statement, which means that my assumption must itself be false. Okay, so let's do that in this specific case. So assume R equals v1, v2 is linearly dependent. All right, so this is the exact opposite of what I'm hoping is the case, that I'm trying to show, which is that R is linearly independent. So let's see what happens if I assume the opposite of what I'm trying to prove. Okay, so this means then there exist numbers. So this is the definition of linear dependence. There exist numbers t1, t2, not both equal to 0. So the number 0, such that t1 v1 plus t2 v2 is equal to the 0 vector. All right, so there's what's called a non-trivial linear combination of v1 and v2. That means a linear combination in which both coefficients t1, t2 aren't 0. Right, the trivial linear combination is when they are all 0, which is equal to 0v. And that's a problem, right? So if I'm allowed to do this, if there actually do exist two numbers t1 and t2, not both 0, which make v1 and v2 add up to the 0 vector, then what's to stop me from writing down something like the following? Then we also have t1 times v1 plus t2 times v2 plus the number 0 times v3 is equal to the 0 vector, right? This is true, right? If this equation is true, so is this equation, all right? And why is that? It's because 0 times v3 is just equal to the 0 vector, right? And it's this left-hand side is t1 times v1 plus t2 times v2 plus the 0 vector. So that doesn't change anything, so it's still equal to the 0 vector. And this can't be the case, right? Because what I've just done is I've produced three numbers, t1, t2, and 0, which make v1, v2, and v3 add up to the 0 vector. And moreover, at least one of t1 and t2 is not equal to the number 0, right? So the set of numbers t1, t2, and 0, one of them is not equal to the number 0. And this is impossible, right? This is impossible because my hypothesis is that S is a linearly independent set, right? And that means exactly that there does not exist any non-trivial combination of the vectors v1, v2, and v3 that will give you the 0 vector. Okay, And so what does this mean? This means that since my assumption that R is linearly dependent leads to a false statement, namely that S is also is linearly dependent, right? This equation is saying that S is linearly dependent. Then that assumption itself must be false, right? So this is a statement which I don't know whether or not it's true or false, right? And I'm saying imagine it's true. Well, if it was, then I would get something false. So it can't be true. It must be false, right? So therefore, I can conclude that R is in fact linearly independent, because if it were the case that R was linearly dependent, this would lead to a fallacy. All right. So that is a nice example of proof by contradiction. And what this is really showing you is that if you have given a linearly independent set in a vector space, then any subset of that is automatically itself linearly independent. So one way to say this that might help in remembering it is that um, subsets of linearly independent sets inherit the property of linear independence. Okay, they inherit the property of linear independence. And if I remember correctly, part C, no, that's not what I wanted to do. Part C is kind of the opposite of this, right? So C is something like show that if S is linearly dependent, then any set T containing S, so not a subset of S, but a superset of S, any set T containing S is also linearly independent. And this is kind of the opposite of saying that linear independence is inherited by subsets. It's sort of saying that linear dependence is infectious. It's kind of the opposite. So if you have a linearly dependent set, and that linearly dependent set is realized inside some bigger set T, then it infects the set T with its linear dependence, right? So it spreads to T, and T becomes or is necessarily linearly dependent. Okay, so why would that be the case? So let's write down S again. So it's just a set of k vectors, v1 through vk. All right, and let's make T an easy looking an easy looking a superset of S. So let's call it something like V1 up to VK. So there's this is S sitting inside T. That's not a very good looking underbrace. So this is the set S. Okay, and then there's some other vectors. Let's call them W1 up to WL, let's say. All right, so this is a kind of the generic way that a superset of a set S of vectors V1 through VK would have to look. And okay, and what I know is that this is linearly dependent. And what I want to show is that so is this. Okay, so let's see. This is a kind of it's a generalization of part A of two. All right, so in part A, my S was a single vector consisting of 0, and T was something bigger. All right, so now I'm doing this more generally. All right, and so what do I have to do to show that the T is linearly dependent? Okay, so I have to um, have to exhibit the existence of scalars. Okay, yeah, and how many of them, right? Actually, k plus l of them, right? So t1, t2 up to tk, and then tk plus 1 all the way out to tk plus l, such that they're not all equal to 0. Okay, and yet t1 times v1 plus all the way up to tk times vk plus tk plus 1 times w1 plus up to tk plus l times w k plus l is equal to the 0 vector. All right, so how can I do this? Well, and I want to do this using the fact that I know S is linearly dependent. Okay, and so since S is linearly dependent, right? So since S is linearly dependent, I can find k of these numbers with this property, right? So since S is linearly dependent, there exist T1 through TK, not all 0, not all the number 0, such that T1 V1 plus TK VK is equal to the 0 vector. Right? That's the definition of what it means for S to be linearly dependent. Okay, so what can I do with that? Let me actually take this over to the next page. So I'll copy that. All right. Okay. All right. So, and these numbers are, these t's are not all 0. Okay. So now the numbers T1 up to TK, and then just 0, 0, 0, right? L times are not all equal to 0. Okay, why is that? Because the T1 through TK are not all equal to 0, right? At least one of these numbers is non-zero. So if I just extend that list by an arbitrary number of additional zeros, it maintains the property that at least one of these T1 through TK is not equal to 0. And now we have that. So what happens when I make the linear combination of V1 through VK and W1 through WL with these weights, all right, with these scalar multiples, right? So I'm looking at the vector T1 times V1 plus T2 times V2 plus up to TK times VK plus 0 times W1 plus 0 times W2 plus 0 times WL. What is this equal to, right? This is equal to something, right? I can actually evaluate this sum. So the sum of the, let's evaluate it in two pieces. Okay, so we'll first sum the first k terms of the sum, and then the last l terms of the sum. All right, so the sum of the first k terms, well, that's I know what that is from this equation, right? So this is equal to 0v, right? So this sum of these k terms is equal to 0v. And what about the sum of these remaining terms? Well, it's 0 times the vector 1, okay, and that's equal to the 0 vector. and 0 times the vector 2, that's equal to the 0 vector, all the way out to 0 times the vector WL, and that's equal to the 0 vector. So I'm just summing up the 0 vector L times, okay, and that's giving me the 0 vector. So this is just 0 vector plus 0 vector, which is equal to the 0 vector. Okay, and so what have I done? I've shown that I can find a list of numbers, k plus l numbers, t1 through tk, and then the remaining l numbers are all equal to 0. But this list isn't just the number 0 repeated k plus l times, right? At least one of t1 through tk is non-zero. And I have, and this causes the corresponding linear combination of the vectors in the set capital T, which is equal to v1 through vk, w1 through wl, right, is the 0 vector, which is exactly the definition of linear dependence, right? So we've shown that the fact that S is a linearly dependent set and that it's contained in T, that infects T with the linear dependence of S, and T is also itself linearly dependent. Okay, so that is lecture 1, just sort of knowing the definition of a vector space, as well as the definition of linear dependence and independence. So these are really the first two concepts in the course. Is enough to settle the first two problems on the problem set, which on Friday may very well have looked totally unintelligible. But you kind of keep them in your mind, and every time you pick up a new concept in the lectures, you apply it to the problems that you're keeping in mind, and you see if it can help. And okay, so what about the remaining problems? Well, the remaining problems they deal with concepts like dimension, okay, which is also considered in lecture 1, right? But let's give it a minute for that to sink in. Okay, so let's be satisfied here with the fact that having some mastery over the first part of lecture 1 is enough to basically dispense with half of the problem set, as long as you kind of understand what you're reading and keep your wits about you a little bit. And okay, so I hope that watching this will be helpful, and I just want to emphasize that what I've written down for you here are not really assignment solutions, right? This is not at the level of exposition that's required when you submit a problem set. You know, you have to really write things up in nice, complete sentences and justify all the details. For example, here, I'm using special numbers like k equals 3 to help my intuition, to sort of help me see what's happening more generally. And of course, you can't do that in a formal solution on the problem set, in a formal proof. You have to show that this is the case for all values of k, not just k equals 3. But what's going on here is that once you know how to do it for one value, you probably can figure out from there how to do it for all values as well. All right, so I will leave it to you to solve problems 1 and 2 in their entirety, and to write down their solutions in a pristine and totally clear manner. All right, and we'll